Well, thanks, Paul. I hope everybody is enjoyed this nice conference and looking forward to a nice weekend and everything. And I hope everybody is staying safe in these tough days. So Paul asked me to give a masterclass in porphyry coppers in 30 minutes. Most people take about a week and a half to do this. So we're going to go really fast, and I'm going to take a different approach from it. And we're not going to spend a lot of time inside a porphyry copper deposit because they're pretty well described and understood by everybody. So what we're going to do is start at the very bottom of the porphyry copper system and work our way up through the magmatic plumbing system up into the porphyry. And then we'll talk a bit about preservation and whatnot. So we're going to jump pretty quickly along in a series of topics. And of course, I'm always available for answer any questions. My email is there on the bottom of the first slide. So the challenge going forward in the exploration for porphyry is to find ones that are not sticking out of the ground like this very nice hydrothermal alteration system in the high Andes of Peru. It's not been drilled, or it wasn't drilled as of about 10 or 15 years ago, but it is sitting there. So there's something still sticking out of the ground. So just to remind everybody of the importance of these magmatic hydrothermal systems, and I've expanded this to include the epithermal, particularly the high sulfidation environment. And really the porphyry copper deposits produce between 58 and 70% of the global production of copper on an annual basis. So they're very, very important. The lifetime of mines are measured in decades and not just a few years. They also are a major source of other commodities such as gold, silver, molybdenum, rhenium, et cetera, et cetera. Along with the epithermal deposits, which are related, they produce somewhere in the vicinity of 25–30% of the global production of gold. So even in the gold space, they're quite significant. Okay. So really what defines the porphyry copper deposits? They're associated with oxidized anhydrous magmas that generally form in a convergent plate margin. We'll get a little bit more on this in a few more slides. Quite commonly, they're on a pre-existing fault mesh. What the faults can't be demonstrated to be active, but the faults are important to their formation. They form over the tops, the apical parts of plutons, and they form along stocks and dikes that intruded through that apical part of the pluton. They're large tonnage, and they generally are low grade, hypogene grade, less than 1%. Although, as we all know, there's a lot of very, very high grade examples around the world, particularly down in the Andes of South America. But the most important thing is really they're huge hydrothermal systems. The footprints outside of the deposit can be as much as 10 kilometers across. So they're giant. And the challenge for all of us in exploration is to find one that's covered. And so you need to understand what's outside the deposit as well as what's inside the deposit. So if we look on a global basis, they're all associated with convergent plate margins. Most of them are in subduction margins and particularly along the western coast of North America, down through South America, around through Southwest Pacific. But there is a collection of them that are becoming more and more recognized and important. They're interior to the continents. These are old, and some of them are along collisional belts, particularly those turning up in the Himalayas, and a lot of those into the Tethyan in Turkey and the Balkans. So this gives a bit of a summary. There is no unique environment where a porphyry copper is generated. They are in a convergent plate margin. It could be a subduction margin. It could be a collisional margin. Both have respectable porphyry copper deposits. They can be generated, they're proposed to be generated through the subduction of a seismic ridge, subductions of discontinuities of the oceanic plate, subduction reversals, et cetera, et cetera. So there's really no unique environment other than the fact that they're largely formed in a shortening environment But when you actually look at the structural evolution of the deposits, really, they're near neutral to transitions in tectonic environment. And in fact, that's required in order to form the complex vein mesh that characterizes an economic porphyry copper deposit. Okay, so let's start with the very bottom. Okay, somewhere down at the base of the crust in what gets called now a mash zone, you have a series of mafic magmas that come in. They start to collect at the lower crust. You start to interact with whatever the crustal column is, and magma starts to rise. It's becoming increasingly clear with a lot of work, detailed work from the igneous petrologists, that there is an intermediate magma chamber. And this is the crucial, in my mind, the absolutely crucial step. Because in here, you get all this magma that's coming up slightly hydrous. It's not oxidized per se. It gets into here and it starts to crystallize, fractionate. It drops out all your anhydrous phases. That starts driving up the oxidation state of the magma, and it starts to drive up the water content of the magma, okay? If the magma is reduced, you start to leave the mantle behind in these upper crustal magma chambers, okay? From this point, it goes up to the upper crustal magma chamber, and this has a very short time frame of a few million years maximum. And it's in here that you start the exsolution, this phase separation, the rise of magma, the rise of the porphyry dikes and stocks into the upper crust, along with the volatiles that have been exhausted. So we're gonna just accept that this happens. We never really ever see this. This evidence is starting to appear in the igneous petrology literature, and we will end up with this part up in here. So we're going to concentrate above this sort of squiggly line. Okay. So is there evidence for this sort of 20-kilometer, 30-kilometer crustal chamber? Well, there is. And the seismic reflection profiles that across the Chilean Andes have this area in here, where the shear waves are suppressed, which means that there's a bit of liquid sitting down here. That is down here in the 8 kilobars, 20 kilometers, 30 kilometer area. And in fact, that's where the mineral chemistry, the mineral geobarometry is saying where you start to get the crystallization of all these anhydrous phases, the increase in water content, and the increase in the oxidation, okay? And that's an important step, which we'll see in a few minutes. Okay? We've all seen this yesterday from Hildebrando, but basically, this is the strontium and yttrium versus the silica content. And what this is really telling you is that the system is sat down here in one of these mid-crustal chambers, about 20 to 30 kilometers paleo depth. And it's fractionated, and it's increased the water content. So you start to get hornblende as the mafic phenocryst phase rather than a pyroxene or whatnot. And you start to drive up the oxidation state. So why is the oxidation state important? Okay, simply because in a normal magma, the solubility of sulfur is very low. It's a few hundred ppms. But an average porphyry copper deposit has quite a lot of sulfur, many of them over 1 billion tons. But you can go through the exercise. If you have even a 1-to-1 ratio of pyrite to chalcopyrite, which is absolutely abnormal, you have to have, for 1 ton of copper, need to have 4 tons of sulfur. So you have to have a lot of sulfur stuffed in the magma in order to generate these giant porphyry copper deposits. So if you do the calculations, most of these upper crustal magma chambers are really in a range of somewhere about 10 by 15 by 5 kilometers. So it's not very much, not very big. In order to get this much of a porphyry out here, the concentration has to be in the thousands of ppm. It can't do it if it's under a normal composition. Okay, so it has to be, because the sulfur has to be in the oxide stage, and you have if sulfur in the oxide stage, that's +6 valence, then it sticks in the magma to a concentration of several thousand ppms. Okay, so as that magma rises through the crust, you have to actually maintain that oxidation state. So that magma basically has to be armored from interaction with any sort of country rock that will reduce that oxidation state. Okay, so if this crust is oxidized, like a lot of parts of the world that are blessed with a lot of porphyry copper deposits, you're going to get porphyry systems. If it's reduced, then good luck, guys. It's really hard for a rising magma to get through the crust without assimilating part of it. There's basically no free passes. And all the zircon geochronology has demonstrated that no magma except for maybe basalts get through the crust without a lot of interaction and assimilation. So this is a key parameter, okay, to understand. So there is some mineralogy in the slide which I took out, which you can get some idea if the rock is oxidized. That's not, magnetite alone is not sufficient because it has both ferrous and ferric iron in it. But magnetite plus titanite, or sphene for the Americans, is a good suggestion that you're in a magmatic system that has potential to be sufficiently oxidized. Okay, enough on that. So we come back to looking at the magma compositions. This is Dixilato's division of porphyry systems, but there is association between porphyry copper deposits that are gold rich versus porphyries that are moly rich, and it really comes back to the original magma compositions. And this comes back to the fractionation and the crustal interaction history that a magma undergoes on its way towards the surface. The more diuretic compositions tend to be a little bit more gold rich, and the more intermediate compositions tend to be a little bit more molybdenum rich and gold poor. And of course, if you go to the granite systems, they're all associated with the molybdenum porphyries that are copper poor and gold poor. Okay. So let's focus now on this upper part. We've talked about all the stuff a little bit down in here. This upper part is the magma's coming up from that intermediate station. It's getting into these upper crustal magma chambers. These tend to form at the paleo depth about 6 to 12 kilometers, sometimes shallower, sometimes deeper. And you have to form a magma chamber. Okay, so the magma chamber, in many of these, you'll see these plutons are late in the magmatic history, because what that implies is there's an earlier set of intrusions that have actually thermally elevated the gradients in the upper crust, such that magma can get into the upper crust and not immediately crystallize and can start to convect. And convection becomes important because that's how you undergo phase separation in this chamber and the collection up in the cupola. And we'll come to that a little bit later again, okay? So we know that porphyry copper deposits are all sourced from some sort of magma chamber down at depth. And this is just an example from the Yarrington district, where they can map out the paleo depth of the different cupolas that have porphyry systems on it. And this is the outline of the old batholith. It's really the outline of the oldest phase of the batholith. The youngest phase all sits inside this. And the porphyries come through these little cupola zones on the top of the plutons. Okay, so if we think about them, we have an active arc. And if we look at the spacing in Chile, northern Chile, or to Chico to Chile, the porphyry systems are more or less spaced about 30, 40, 50 kilometers between the individual centers. And that's more or less the spacing of active volcanoes now. And this somehow has to be due with the dynamics of magma rise from deep in the crust up to the upper surface. Okay. So here we are, we've built a magma chamber. There's some volcanics up here, country rocks over here. There's an older phase out in here that is very texturally heterogeneous, which really elevated the geothermal gradients in the country rocks. You have another phase in here. But the youngest phase forms these sort of mushroom-shaped plutons down here at depth, and they convect. Okay, and the magma, as the magma is rising, because you're decreasing the load on the rock, you start to undergo phase separation. That's a less dense fluid. It rises and collects in the apical parts, and these are the cupola zones. Okay, so this over here is an example. This is the contact on the margin of a cupola, sits over in this area, and this rock, it's a knife-sharp contact here. There's a bit of flow foliation along the margin, and there is a alignment of the mafic silicates in here. It's just completely been cut off. So these things are undergoing convection, they're undergoing roof erosion and assimilation of rocks. Okay. But at the same time, the fluid is collecting up in the roof here. You're increasing the fluid pressure, and it essentially will have to crack, and we'll get to that in a minute here. So what's happening is in the roof, you're collecting this volatiles with fluids and a lot of low density crystals, such as the pyroxene, no, excuse me, the feldspars. Okay, and you're also collecting all the incompatible elements, acids, and your sulfur and your elements, I mean your metals. And okay. So porphyries, as we know, are the history of multiple intrusions. And what we do know from mapping these porphyries, the plutonic systems that are tilted on their sides, is the dikes or stocks. The first one comes out of rocks closest to the roof. Next ones are a little bit deeper. Next ones are a little bit deeper. So the fluid that starts here and is going up gets to this point with a different physiochemical conditions. The fluid here arrives with a different set. Fluid from this point arrives with a different set. This gives you that overprinting hydrothermal alteration assemblages that we all know very well. Okay. So, and the porphyry sits over the top. So just to give you a sense that really the porphyry magmas are the passenger on the bus. They're coming after the fluid. The fluid is going in front of them. Just to give you an example of this, this is from the E27 open pit in North Parks. Rio Tinto has now filled this in, which is a real shame. They filled it in as a very convenient tailings for them. But for those mapping it, you really only need two colored pencils, one orange and one dark. You can take your choice of the dark. But this, we went right after a rain, and you can see the really dark bands here. They're very much associated with the dikes. The dikes, they're a bit of an arrow here. There's another set over here. There's another set over here. But if you go from this point and go out, the density of these black bands, which is really being driven by the recent rain, and hence the fracture density, vein density, diminishes as you go this way. So these things are very much controlled and being formed in front of the magma, and the magma is just using them as a low as a permeability avenue to rise towards the surface. So just to not leave everybody alone, aside, one needs to basically look at the hydrothermal alteration assemblage. This is a well-known feature, and really it's a product of multiple intrusions. And the cartoons we all draw are an average of what you see. And basically you have the early potassic, which gets overprinted successively by the lower temperature hydrothermal alteration assemblages that are associated with dikes and stocks that start progressively deeper in the crust. Okay. So how do these assemblages form? They're really, the fluid is coming out at high temperature, 650, 700 degrees. It is stable with K feldspar and biotite, so it starts to alter the minerals that are out of equilibrium with those minerals, and it generates your potassic alteration. As it cools, it hits this tie line where you start, depending upon the depth of formation, the SO2 starts to disaggregate and dissociate and gives you acid, and then it drops off into giving you acidic alteration. And depending on the buffering capacity of the rock, you'll either go through to the low temperature clays or through to the advanced argillic assemblage. The geothermal system circulating out here is always rock buffer. This is fluid buffer. And then basically, all you're doing here is adding water and CO2 to the rocks. And they are basically just stirring up. It's like making a cake. You'd add milk and put it under temperature. Okay. So in the process of doing that, you actually transport and remove and transport a whole host of metals. Okay. All these diagrams are available in a recent SEG newsletter, but basically you get an area where you're depleting low valence elements that were originally in the rocks, and they're being transported away. And once you leave the more neutral pH environment of the potassic alteration, you start generating acid, you start precipitating in with the sulfides, a whole host of different elements that come out based upon their solubility in terms of their temperature. Okay. All right. So I'm going to give you a different way of looking at that. That's the same diagram we looked at it. The copper is coming out here. Molybdenum is quite commonly sits in the more acidic environment. You got bismuth, tellurium, arsenic, antimony, mercury, and thallium, all up in the much more lower temperature environment. Okay. So if you've got maintain your rock buffering capacity, you will get all the base metals that form the well-known halos that surround porphyry copper deposits. Why this is important is to understand the temperature of these elements, is you can actually use them in your exploration geochemistry to tell you give you some idea where you are in the hydrothermal system. Okay. Also in the weathering environment, these elements are from compounds with oxygen, and if you've got any acid, these elements are stripped. Okay. So very few people will look at these elements and actually get them at the proper low concentration. But these elements sometimes can be very, very useful. Okay. So enough of the geochemistry, enough of the hydrothermal alteration per se. Let's look at a bit bigger picture. So porphyry districts, and here's just 4 examples. They're actually formed in very short periods of time, 1 to 4 million years maximum. But they all have a common dimension, which I find somewhat remarkable, in that each of these are now put at a common scale bar, of about 5 kilometers. And, they extend over about 5 to 6, maybe 7 kilometers distance. Okay. And if you remember back to the magma chamber is twice to 3 times that width. So basically, this becomes a search parameter, is if you're finding one, the spacing is 1 to 2 kilometers between those two, then, that becomes your search parameter in an exploration camp where you think you have porphyry copper deposits. Okay. So within these camps, what people have noticed is all porphyries don't have the same trace metal. Okay, some may be copper rich, copper gold, copper moly, copper only. And really that comes down to these cupolas that we mentioned earlier. At what depth do they form? So in this case, this porphyry system came out of a cupola at a shallower depth, and this came out of a deeper depth. So because the magma is crystallizing from the margins in, elements that are compatible with the magma and want to stay in the magma will stay as long until they're basically evicted, they're kicked out. Okay, molybdenum is one of those. Okay, copper and gold are quite happy to depart, and so they will leave early. In this case, the Arrington mine here and the Ann Mason deposit here are only separated by 1 kilometer in distance, but their cupolas are separated vertically by 1 kilometer. They had no molybdenum in this deposit, and this has enough molybdenum to be economically interesting, although it's not of high enough grade. Okay. So just give you a taste. This is the cross-section in Redbed dip. They're 4 porphyry systems, all formed in less than 1 million years. Okay. And you can see the various different porphyry dikes. They're not all created equal. Okay. They all have different aspects. Okay. These are the 2 systems at Redbed dip, which form the economic deposit here. So if we look at the hydrothermal alteration, the distribution of the hydrothermal alteration is quite distinct, and that pinks are potassic, but particularly where the paler pink is, you have quite a lot of lower temperature chlorite sericite that overprints on it. Okay. Whereas the H79 deposit is no grade, and this has a bit of grade here in the H13. Okay. If you then add the sulfide assemblage, you can see the sulfide assemblage is quite different as well. H14 clearly has a lot more bornite. It's higher grade, of course. If you go back, oops, it has a lot more of the potassic alteration that goes all the way to the surface, whereas H15 is lacking that. Whereas H15 is dominated by chalcopyrite with a bit of bornite. Okay. So these reflect different chemistry of the fluid coming out of the magma chamber. This, in theory, would have been first because it's the oldest, or this would be first because it's the oldest. This is second, this is third, and this would have been last. It's only 4 kilometers here. So it's quite well within that 5 to 6 kilometer range that we talked about. So they can be very different once you get into a camp. Okay, so in these porphyries, as we saw, the porphyries and the vein mesh is really, really intimately tied together. And in fact, when you go to the physical volcanology world, what you can see is that there's hydrofracking going in front of rising magma. They can map this out using the microseismicity, and these intrusions can go for quite far distance. Okay, but the porphyries are very much intimately associated. In each of these diagrams, this is the porphyry contact, and this is just vein density and frequency. This is a small one in North Parks. Really goes out about 100 meters. Whereas you go to a giant, you're at Bingham. These are various types of quartz veins. Quartz stockworks, those are the copper ones. The blue is the molybdenum ones. These are your late D-type veins, quartz sericite, pyrite, and then of course the total. So then they go out almost 2 kilometers from this stock margin. So a lot more fluid in the giant deposits than in the smallest one. Just to bring you back to how that correlates to grade. Vein density correlates with grade 1 to 1. I mean, that's what we all look for, is map the vein density, map your volume percent, and follow the strike and dip, and you'll eventually get to the porphyry, hopefully. Okay, this is just John Prophet's map from Baja de Alhambra. in Argentina. There's some faulting in here. The blue lines outline some low grades. These are probably late porphyries. Green outlines relatively decent grade, 0.5% copper. But the really high grade copper is associated with the highest quartz vein density. See, greater than 50% volume percent quartz veins. Okay. As you will see, this is not always the case. There is some higher quartz vein density, but it's well within the 0.5% copper. So there is a characteristic vein orientation that goes with well-mineralized porphyry copper deposits, and this is the so-called stockwork. Stockwork, as a structural geologist, drives me absolutely bananas and crazy when people just say it's stockwork and there's no geometry, and it's not true. Okay, there are enough studies that demonstrate there's quite a consistent geometry to porphyry stockworks. And quite commonly, it eventually resolves itself into some sort of orthogonal geometry. So in order to have an orthogonal geometry, you have to have a relatively low differential stress, such that veins can dilate in this direction, and then you interchange your principal stress geometries and will dilate in that direction. Okay, this is very common. Sometimes one is a conjugate, sometimes it's a straight vein, but basically that geometry virtually always goes with decent grade porphyry copper deposits, except those that are formed in a breccia environment. Then that's a different kettle of fish. Okay, so that's enough on the porphyries per se. So if we step outside the porphyries and think about how we're going to find one that might be under cover, the late D veins, and D veins are basically quartz sericite pyrite veins, quartz veins with sericitic and pyritic halos, and they will carry a lot of your lower temperature pathfinder elements, the bismuth, tellurium, arsenic, etc., as we went up earlier. In some places like Baja de Alumbrera, they form more or less a radial pattern with some concentric vein geometry. Whereas others, and that's out maybe 1 kilometer, but in others such as El Abra in northern Chile, and this is a photo of those things, these things will go from 5 kilometers away and quite extensively. Okay, the deposit is up here, and these lateral D veins go a long way away, and they become your exploration guide as you to look for additional resources. Okay. So in this quick half an hour, I say I'm not too much over time, Paul. We've actually done from bottom of this slide, actually below this slide, up through this. And we touched on a few aspects of the porphyry copper deposit per se, a few aspects of the magmatic system, few aspects of the important step way down here in the upper crust. We've pretty much left the epithermal environment aside, and there's a good reason for that, because what happens if the fluid leaving from here has an exit path, that is a place that it can go pretty fast up towards the upper crust, upper 1 kilometer, then what's happened logically is that the fluid is passed through the porphyry environment and it gets up into the epithermal environment. There's nothing wrong with that. They're quite nice deposits. But the question of whether there's a porphyry copper deposit at depth still is an open one. There's some decent evidence in some places, and there's other places there's absolutely no evidence whatsoever. Okay. But the last question I want to leave you with, particularly from the exploration perspective, is the preservation. Okay, we all know that most porphyry systems, and as for most epithermal deposits, are relatively young. They're Cenozoic, less than 70 million years. And that's really a function of tech. But we also know, we also know that there's some very, very significant deposits that are Paleozoic, such as the one in the Altaides in Eurasia, down in the Acadia district in Australia, and up in the Kazakhstan. And there's just some, some very nice and old deposits. And really the preservation of an old deposit or any deposit is a function of the tectonic environment, what sort of climate that they were put into, and of course time. And I'll give you an example here from Dave Braxton and his work in the Boyongan and Bayugo district in the Philippines. And that these deposits were placed, about 2 million years ago at about 1 kilometer depth, the top of them. They were outcropping and eroding and within 4 million years, and then buried again. Okay, so if you just do some rough calculations, the exhumation rate is just about at 2 millimeters a year. So on a global basis, the exhumation rate's about 1 millimeter a year. So it doesn't take long in 1 million years to remove 1 kilometer of crust. So the key really in this is when you get into a porphyry system, you have to start thinking about what's happened to it subsequently. Okay, because there may be pieces of it that have been detached. There may be pieces that are sitting under gravel that you don't know about, or younger rocks. And it may be tilted such that, if you drill a vertical hole, oh, boo, all of a sudden you drill out into the marginal alteration assemblage. I have been on ones that they were wondering why they drilled a vertical hole and they ended up in the marginal. Well, it's because it's on its side. It's very simple. So it's really important to think about the post-mineral history as well as the syn-mineral history as well. So I think I'll quit there, and I'll leave you with one last slide. I wish you all buen éxito in the exploration program.
Thank you very much for the invitation. It's really great opportunity to us to have presentation. It's so far country like Colombia. Unfortunately, I'm a bit nervous because I don't like talking to the computer. So that is my problem. And the next problem is probably I incorporated too much number of slides. But anyway, I will try, first of all, to introduce you, very young geologists from Max Resources. They are like Alma, Paula, Marvin, and also senior geologist Piotr Lutyński. And next two person represent AGH University. It is AGH University of Science and Technology, more than 100 years university located in Kraków, Poland. Okay, the structure of the lecture is very simplified. At the beginning, I would like to talk you on the discovery. And there was a lot of discovery which took place in the last 20 years. But discovery in Poland is a little bit older. Of course, the Kupferschiefer in Europe is very old, is very well known in all people living in the Kupferschiefer, living in Europe, especially geologists. Especially in German basin, Kupferschiefer is known since medieval time, I guess. In Poland, new discovery took place in '57, and after a presentation of Colombian discovery, I will be talking a little bit about the Kupferschiefer. However, usually electron Kupferschiefer takes much more time. 1 hour is a minimum to explain a genesis of the Kupferschiefer. Sorry, I would like to make everything what is possible to give you enough understanding presentation. Similar presentation took place in Ecuador, also in 2019, and in much earlier in Peru, 2006, as the next discovery of 2019. Please have a look for these pictures. The first from the left-hand side is showing massive copper ore from deep underground mining, Rudna mine in Poland, and it is very similar example of high-grade copper mineralization from Colombia, and also very rich in both metal, I mean copper and silver oxidized from the outcrop also in northeastern corner of Colombia. Please compare these slides. These slides represent sample collected from different places of South America. First is to the top, left to the top is sample from Max resource. To the right is Aurania resource from Ecuador. To the down left is Hanan Metals. It's the name of the company, but also from Peru. And the last is also from Peru, but it's Mitu formation. All these samples are very similar and are collected in different places. And this green line here is showing outcrops of Jurassic sediments containing copper mineralization. These two slides show you a size of economic grade deposit in Poland. And this line shows us extent of Kupferschiefer, or there is some, I see some information about there is some trouble with internet, and the picture from the right-hand side show you comparison of size of Cesar target to Kupferschiefer mining area. It's almost very similar. Okay, here from the left-hand side you see fields or targets, different deposits in Poland: Lubin, Polkowice, Rudna, Sieroszowice, and deep industrial Głogów. Here we have phosphodatic monocline. It is gently dipping to the northeastern corner. Jurassic sediments containing copper mineralization are also dipping gently to the northwest, west, and southwest direction. The sediment-hosted strata-bound copper silver mineralization was discovered previously in 2019 by geologists of Max Resources, and there in next year there was of course collected much more sample. So also in our office in Krakow we have some sample from these deposits. However, we have 15,000 sample for comparison from the Kupferschiefer type mineralization. And we decided to part and to help recognize especially mineral system which is related to the Kupferschiefer and which was that was found also in Colombia. This left picture down show very fine, very good outcrops containing 7.19% of copper with some silver, and this from right hand side very exciting sample containing high grade oxidized type of ore. The next slides will show you some of course outcropping with channel sampling showing you the copper content, also high grade copper mineralization. Next is very similar, high grade 2 meter, 6.25% of copper and 45 grams of silver. Next is 1.2 meter thick outcrops containing almost 4% of copper and 35 grams per ton of silver, and representative from right hand side this sample is coming from this outcrop here. Next, copper mineralization is relatively lower in comparison to our other, but the grade of mineralization is still enough high. It is of course economic grade of copper mineralization, which includes also some silver content. And the representative sample is coming from this. This outcrop is a little bit dark because it's after, let's say, very, very intensive rainfall, I guess. Position of the discovery is shown in this profile. It is La Quinta formation composed of sandstone, shale, and volcanoplastic, and position of Stratabound copper silver mineralization is marked in red. And from the right-hand side, you can see typical type of ore, especially chalcocite rich, which is marked here, and very high-grade ore, 20.9% of copper, and also high-grade silver content, 171 gram. It's very high concentration. And La Quinta formation is covered with this unconformity by clitty shows sediments composed of limestone, shale, evaporates, but also in the upper part is possible to find also rock salt domes, which are related to the clitty shows evaporates. Okay, next slide will show you construction of structure of the basin, and in orange color are orange color is representing position of the copper bearing, let's say, plastic sediments containing high-grade copper mineralization. Of course, our information to this project are coming from the outcrops, which are presented in many places in northeastern corner. And in blue color, these are sediments of Jurassic sediments. If we compare two different cross sections, the left cross section is through the Polish Kupferschiefer system, the right is from Cesar Basin, is really, it looks very similar. Here in this basin, we have evaporates to the right-hand side, this blue color, and also in Poland, we have evaporates which are above the Kupferschiefer system. Also in the bottom, we have some plastic carboniferous and Permian beds seek up to 800 meters. It's very important information. And between the Kupferschiefer and evaporites above is continuous mineralization and continuous sediments are presented. Kupferschiefer itself is a horizon, but for us, it's not only the horizon, lithological horizon, but it's also the system. The system is responsible for the concentration of different metals. It also the system is responsible for forming redox barrier. This redox barrier is very important here. And Kupferschiefer itself is sediment, is fine-grained plastic sediments containing carbonate and clay minerals in 30% probably in average, and also organic matter up to 30%. This organic matter is of sapropellitic origin. Very similar situation we have in Colombia. However, we have no enough time to examine organic matter, but the situation in the profile is very similar. We have plastic sediments with high-grade copper mineralization, enough big silver, which correspond also to the high grade of copper mineralization. From the Polish system, there is annual extraction of ore is on the level 30 million tons, copper ores grading 1.63% of copper and 46 grams per ton. It gives possibility the KGHM company is the world larger silver producer and the 8th copper producer. So it's really very important. But this, for me, first of all, this profile are geological profile and geological situation are very similar. And the mineralogy of the Colombian discovery has probably two different associations. One association is metallic native copper together with hematite. It is coarse-grained hematite. And the next type of association is probably deeply altered sandstone containing copper sulfide mineralization. This white material here is chalcocite and blue covalite, but also you can see here this crystal, this white crystal with a little bit higher relief is also hematite. But this hematite is a little bit different if you compare it to this associated with copper, with native copper. And let's go to the Europe. To the Europe, this red line is showing you the extent of Zechstein sediment, extent of intercontinental Zechstein Sea. This copper is distributed in many places, but especially copper is concentrated in southern wing of the basin. The scale you can see here, altogether probably it's 1 million square kilometer basin. In Colombia, you have probably 2,000 long this Jurassic sediments containing occurrences of copper-silver mineralization. In details, this important copper concentration within the Kupferschiefer are very well recognized, especially in German basin and also in Polish basin. The names are listed here to the right-hand side. In German names, we have joint project with one of German company. It is Spremberg-Weißwasser, but this L is Lubin area and NP is North Sudetic Trough, containing old copper mining district in Poland. For the beginning, I will explain you especially, I will show you some cross-section through this old system, and then we will go to the Lubin system. And here in German profile is barren profile. We have a very simplified section containing porphyry in the bottom, overlying by Zechstein conglomerates and Vera limestone and so on. This slide from the right-hand side is coming from different area, but in this case you have Kupferschiefer, highly mineralized with sandstone, fine-grained laminated sandstone containing chalcocite mineralization. It's also from German. In Polish Kupferschiefer, the section is very simplified. It's coming from the deep mine. You have sandstone ore, we have Kupferschiefer type of ore and dolomite type of ore. In the North Sudetic Trough, in the syncline, we have cross-section, the green showing us position of the copper deposit. Copper deposit is not very high grade, 0.8086, 0.9095, and so on, with several grams of silver. But what is important from this section? Deposits is pinacordant to the lithology. Copper deposit is pinacordant, is cross-cutting lithological linear here, and it is slides from the open print from Nowy Kościół mine. And some details, we have maroon colored Mars, and above we have copper mineralization grading 0.56%. And details from the left-hand side is oxide mineralization containing some copper carbonates. The very similar profile is from Grodec syncline. The copper deposit is cross-cutting the lithological units which are listed here, and copper Mars are like this. And mineralization from this copper Mars is very well visible on these micro photographs, especially interesting in this left up left corner, showing you chalcocite mineralization with bornite, silver-bearing bornite, and with some native silver located here, and the other showing us some replacement. And let's go to the Lubin. It is Lubin area containing several mines. Each this square here is separate mine. In fact, the size of this of each area is close to 100 square kilometer. Here in green is additional reserves area containing altogether, probably the size of this area altogether is more than 900 square kilometers. Can you imagine the deposit? The size of the deposit is 900 square kilometers, but we have much more such economic grade mineralization located within the Zechstein Basin. And this is Rudna mine, located in this place, very big, one of the biggest underground mine in Europe, extracted 11 12, sometimes 13 million tons of copper grinding 1.4047. Profile in Kupferschiefer profile. Kupferschiefer is very simplified. We have plastic sediment, device ligandes, then we have Kupferschiefer layers, and Zechstein limestone, which in fact is dolomite. And this profile to the right-hand side is coming from different sections, coming from the west south corner of the deposit is secondary oxidized system containing gold mineralization. And gold mineralization is related to the oxidized system. And copper deposit is shifted upwards, but the copper mineralization is not so high grade like related to the normal typical profile of the Kupferschiefer. Cross section through the deposits, this line is based on a realistic profile from the copper mine, from the Rudna mine, showing us a huge ore body. The thicker ore body is related to the section without Kupferschiefer. As you see, the Kupferschiefer is not only factor, not only unit controlling the copper mineralization. In such situation, we have really deposits which the thickness of these deposits in some places is 20, even 6 meters. So accumulation index from such place is more than 1,000 kilograms of copper from 1 square meter in such places. And normal accumulation is just above 100 kilograms. And some picture from the Rudna mine. This is mining galleries here, and showing you some dispersed type of mineralization, spotted type of mineralization, and two different type of mineralization. This primary and secondary enriched massive copper, massive sulfide are presented like here. This distance is 4.5 meters. Next details, the Kupferschiefer is almost missing here. We have only a sign of Kupferschiefer, and this black dark material is chalcocite enriched sandstone. And here we have also laminated sandstone, which represents the first stage of mineralization. Above, we have dolomite. This dolomite contains also some sulfate mineralization. Some different picture from Rudna mine. You have texture. This is a structure from such like similar to chimney, to the pipe, and tectonic system with vein type mineralization, with massive type of mineralization. And this massive type of mineralization is reflected light, show us the texture and structure. These are white material is chalcocite, which replace not only the cement of sandstone, but also replace chalcogenic grains of feldspar, and also in some places quartz. Here, as typical profiles which are showing us relationship between silver mineralization and copper mineralization, is very well correlated system, and silver content, maximum silver content is related to the Kupferschiefer mineralization. And here you can see white is silver and brown material is bornite, and sour replacement are very common. And this picture to the right-hand side is coming from the sandstone. What is important here? You can see autogenic quartz, and autogenic quartz is a part of the cement of sandstone, and the younger is chalcocite, is massive chalcocite, which cemented everything. Next system showing you the next section. I would like to show you the secondary oxidation system, which is the bottom. This part is secondary oxidized. This part above is copper deposit. And in this system, we found gold mineralization. This hematite, which is hydrothermal hematite, containing 2% of gold. And this is native gold of very high purity, 98, 99% of gold in gold. And also, this is maroon shade, this black typical shade, Kupferschiefer, is converted to the maroon shale, which maroon shale contain gold mineralization in the bottom. These circles, in each circles are occurring gold, is occurring gold and hematite association. Also in sandstone, these circles show you position of gold mineralization, and this line show us that this gold mineralization is probably of hydrothermal origin, and tectonic took place important role in distribution of elements. And replacement, these are very common in the Polish type of Kupferschiefer. It is boundary dolomite, it's just below the Kupferschiefer, and sandstone, which is occurring in eastern part of the deposit. And it is, this massive is chalcocite. And here is lingula. Do you see? This lingula is replaced fully by the chalcocite. These black dots within the chalcocite are relics or dolomite, which is replacing by the massive chalcocite. Kupferschiefer, please have a look at different type of mineralization, different style, different texture, different kind. This is a lot of tectonic and some nest type of mineralization, and is a lot of dispersion. And it is special type. This Kupferschiefer containing tectonic mineralization. This tectonic mineralization is very common. In many places, it's possible to find such example of tectonic information. A special type of Kupferschiefer. It is calcitic type of Kupferschiefer. In the bottom here, we have a pieces of sandstone, and above this black material is dolomite. And please have a look how many tectonic lines. These tectonic lines are fulfilled with chalcocite mineralization, which is evidence for really tectonic development of the basin. It is a very gentle angle cutting of the Kupferschiefer, very soft material. What is important? This Kupferschiefer calcitic type is barren, and after dolomitization, there was 13% of volume free space was released, and then in Kupferschiefer we have just up to 30% of copper mineralization. Of course, in places of secondary enrichment, the copper mineralization in Kupferschiefer can reach even 30%. And
Adam,
what is
last 2 minutes, please, Adam.
Okay, I hope I will finish everything. And then we have dolomite type of ore. What is important here? We have sulfate, and this sulfate, in the sulfates is chalcocite of framboids of chalcocite. Is a little bit bigger picture is show you separate crystal of chalcocite, which are of organogenic, probably bacteria which are cemented with chalcocite. And gypsum and dolomite relationship is very well visible here. Next is exploration map, new exploration map. You have mining system here, old mining, copper mining system in Poland, North Sudetic Trough, and these red circles show you next economic accumulation of the copper and silver. Altogether, the active deposits have 65 square kilometers, reserves 500 kilometers, and new documented areas 750 kilometers. As you see, you have huge system containing high-grade copper, silver mineralization, and also nickel, cobalt, lead, zinc, uranium, a little bit moly, and also thallium and PGMs. And let's go to the Peru. Please have a look. It's very typical red sandstone, exactly the same like we have in Poland. It is Me2 formation containing shale, containing very high-grade copper mineralization, also from Peru. Please have a look. It's very typical sandstone. This is exactly like in Polish high-grade ore containing more than 10% of copper, and is typical organic material which is represented in whole Jurassic basin in South America. And going to the final point and final, let's say, conclusion. In our opinion, there is a huge discover sediment-hosted copper-silver belt in South America, 2,000 kilometers probably long, with many, many outcrops containing high-grade, economic grade of copper-silver mineralization. What are similarities between Kupferschiefer and this basin? Basin character, lithology, geology, also tectonic, mineralogy is very similar. Deposit parameters are also similar. As you see, high grades of copper mineralization. And what is important? We did, one of the university did for us first isotopes, sulfur composition. It means this kind of sulfur is very similar to Kupferschiefer basin. In Poland, we have close to even minus 35 promils, but in Colombia it's very, very similar. It means the system of sulfur and source of sulfur can be similar in both basins, the South American or also in European type. And new sediments hosted are discovered in South America, as I mentioned also before, by 3 different companies, Max Resources, Aurania, and Hanan Metals, Peru. This basin can be really compared very easy with system existing in Europe, which is much better recognized. By hope that we'll have still opportunity to work with some geologists from Colombia. So thank you very much for your kind attention. But at the end, I would like to show you what is important. This is my last slide, showing you high thickness of deposit, copper deposit located in sandstone. In this section, that was 8 meters of sandstone, and excavations show us and the size of dimension of these mining galleries is the size of the geologist is here. Is 2 meters is here. You can compare a machine working down. This white material is sandstone containing copper mineralization. Thank you